Hi everyone. This section is all about polynomials and rational functions which use polynomials in them. So you definitely talked about polynomials before, and we've actually learned about some already. For example, linear equations are polynomials. Same with quadratics. And we'll come up with an exact definition for these, but these are honestly one of the most fascinating parts of mathematics that I've ever learned about. There are so many intricate and detailed patterns with polynomials. They're just so interesting. So I'm really excited to talk to you about some of this stuff. So for the sake of notes, we're going to talk about characteristics of polynomials. How are they used to model situations? Most applications of polynomials involve linear functions and quadratic functions, and sometimes cubic, but once you get beyond that, that's really just more dealing with abstract mathematics, which is cool in its own way. You know, things don't have to be applied to be awesome. So we're going to talk end behaviors. We're going to talk weird shapes of graphs, which you've likely seen before. For example, the W graph or the M graph, something that looks like this, or something that looks like this, or anything in between. We can write functions for all of those, actually. So it's pretty cool there. We're opening up some doors. And then we're going to talk asymptotes again, and that ties into our rational functions portion. So let's talk some vocab, and then we'll kind of talk about the concepts before I officially give you the notes for them, so that you can kind of understand some of the history of polynomials and some of the really interesting patterns that we find within polynomials. So let's talk. Okay, I'm saying this word a lot. What is a polynomial? What even is that? A polynomial is a function in the form p of x equals a sub n, which is just a constant term, so a number, 1, 2, 3, -8, 4/3, x to the power of n, plus your next constant, your next coefficient, that's an n, a sub n minus 1, times x to the n minus 1, and you might already see a pattern, and then we're going to do a sub n minus 2 times x to the n minus 2. So I'm just going to do some dots, a sub 1 x to the first power plus a sub 0 x to the 0 power. So a polynomial, you may have heard the term monomial before, M-O-N. A polynomial is just a combination of the sum of one or more monomials. So each of these terms is a monomial. So it could just be one of them. It could just be the last constant term. So it could just be y equals 5 is a polynomial. So I'll write some examples. So it's like y equals x to the 4th power minus x squared, or y equals 5 minus x, or even just y equals x, or y equals 5. One thing that is important that I didn't tell you, these n's have to be whole numbers. Okay, I should say n is a whole number. How about that? Which means it has to be a positive whole number, because whole numbers are numbers 0, 1, 2, 3, 4, 5, 6, all the way to infinity, right? They approach infinity. Infinity is not a number. Okay, which means that if you have 3 times the square root of x, this is really 3 times x to the 1/2, not a polynomial, because that half is not a whole number. Or let's see, 3 over x. Hey, that looks like it's x to the first power. But y'all, it's in the divisor, so it's being divided. So this is really 3 times x to the negative first power, which is not a whole number. So not for that guy. That's not a polynomial, just by definition of what a polynomial is. it's a different kind of function. In fact, it's actually a rational function. It's not a polynomial. So now a rational function is two polynomials divided by each other. So polynomial q and p. So p of x divided by q of x. So just two polynomials being divided by each other. You've seen things like this before, where p and q are polynomials. So this is like something like what I just gave you. 3 over x is not a polynomial, but this 3 is a polynomial, and this x is a polynomial. Therefore, it's the division of two polynomials, so that is a rational function. And this term rational, I just crossed that out. A rational function uses a definition of a rational number. If you remember, I think you did this maybe in 8th grade. Categorizing numbers based on what they are. So like whole number, rational number, natural number, a real number, complex number. A rational number is a number that can be written in the form m over n. So it can be written as a fraction. And that's where this comes from, because this polynomial can be written as a fraction of two polynomials. Excuse me, this rational function can be written as a fraction of two polynomials. Or you might have something more complicated than this example. You might have like, just for example, 3x squared minus x all over 4 minus x. As long as you have a polynomial in the numerator, polynomial in the denominator, you're good to go. Okay, and we've talked about this before, but we'll chat again about asymptotes. They come into play with our rational functions. So vertical asymptotes are vertical lines which correspond to the zeros of the denominator of a rational function. For example, this guy is going to have a vertical asymptote whenever we can get this denominator equal to 0. So that is when x is 4. So this means x equals 4 is a vertical asymptote. Or in this example here, this denominator will be 0 every time x is negative 3 or when x is 1, because that will make the denominator 0, which is where the function is undefined, so it creates vertical asymptotes at those lines. Now, a horizontal asymptote is a horizontal line that the graph approaches as x approaches negative infinity and as x approaches infinity. So as x goes left and x goes right, does it approach some number? I'll clear this. Okay. So horizontal asymptotes actually can be crossed, for example, in this function here. To find them, degree. If the degree, which is the largest exponent of the denominator, is larger than the degree of the numerator, then we have a horizontal asymptote, which is which is the x-axis. So vertical asymptotes deal with the zeros of the denominator. Horizontal asymptotes deal with the degrees of the numerator and the denominator. And vertical asymptotes will never be crossed. Horizontal asymptotes can be crossed because all we're really looking for, these are just a value that the function approaches as x grows to infinity or as x grows to negative infinity. All right, and yeah, before I dive into this, I want to talk about some other interesting properties of polynomial functions. So here we are on a PowerPoint now. And I kind of broke up the notes on this PowerPoint, so we've already talked about that and that. Okay, and we did this in class. I'm not sure if this will work for you. I'm not sure. I tried a new tool to have interactive slides to get y'all online interacting with the students in person. And it's new, and I'm not sure if it's going to work, but try it. Try to join. Try to go to joinpd.com and type in this code. If it doesn't work, then I'm sorry. I'll walk through it in this video. Let me know if it works or not, though. Because I would like to get you all interacting with the in-person students a little bit more, just so you don't feel so disconnected, if you even feel that way. Okay, so for the sake of this video, Let's create some polynomials that go through the point 0, 0, which means it has an x-intercept at 0. Another word for x-intercept is 0. And another word for x-intercept is the root. So find the root of the function. That's the word I prefer to use, the root of the function. Okay. Polynomial. This can be anything. Y equals 0 is a polynomial that goes through the point 0, 0. Y equals x also goes through that point. Y equals x squared. Whoa. They all go through this point. Anything where if you plug in a 0 for x, you get 0 for y. So y equals x squared minus x will also get you through the point 0, 0. This is just kind of an interactivity to the zeros of a polynomial. So you might say, okay, what's the point of this? Here we go. Let's try another one. Let's create a polynomial of at least third degree. So that means we're going to have an x cubed term that has a root at x equals 1, which goes through this point x equals 1. So if you go to the pear deck thing, then you'll be able to actually answer this question. But if you can't, then just pause the video, try it on your own. Here. All right. So I assume you found your own, and students have had lots of different solutions for this one throughout the day. One common one was x minus 1 cubed goes through this point, which this was literally just a horizontal shift 1 to the right. So that means this inflection point right here, where we switch from concave down to concave up. That's called an inflection point. We're going to learn all about that in like a month. All right. So this inflection point is now at 1, 0. And there were so many other options here. So we'll just keep going. Okay, now this is really where we get into the key of things. So create a second degree polynomial. So that means you're going to have an x squared term that goes through the points 1, 0 and 3, 0. So this means the roots are at 1 and 3. So go ahead and pause this video. Just experiment on Desmos and try to find this polynomial. All right. And whatever you had. Oh, man. Okay. For the sake of this video, I will share one of the polynomials that was found during class today. So this was x squared minus 4x plus 3. We got our roots at 1 and 3. So one interesting thing about this is what happens when we factor this. And this is one of the really cool parts about polynomials. So if we factor this guy, this is going to be x. Remember, factoring, we factor out two different terms. And we're going to multiply. Okay, so we're trying to find a number here and a number here that multiplies to 3. And they add to -4. And since this guy's positive, this guy's negative, it's going to be x minus and x minus because we're multiplying to 3. So to get a positive 3, they either both have to be negative or they both have to be positive. But we have to add two numbers to be -4, which means the numbers both have to be negative. And now, what two numbers multiply to be 3 and add to be -4? Well, -1 and -3. We only have so many factors of 3. Y'all. X minus 1 and x minus 3 is the same thing as this guy. And I'll even write that into Desmos to prove it. X minus 1 and x minus 3, same line. Our roots are still at 1 and 3. So the really cool thing about polynomials is you can write them in terms of their roots. So this quadratic can be written in terms of its roots. So this can be x minus 1 times x minus 3. And then that immediately shows you where the two roots are. Another thing to notice, how many roots does this quadratic have? It has 2, which might have something to do with the degree of the polynomial. But we'll keep going. Okay, the next one, this guy, finding the zeros. We can graph this, which I will do. So that was x squared minus 7x plus 12. Where are the zeros? 3 and 4. Can we do this algebraically? You betcha we can. We can factor this guy to x minus 3 and x minus 4, which are the roots. Remember that factoring is just the opposite of distribution. So we can write polynomials in terms of their roots. We'll go back algebraically. We can write this as y equals x minus 3, x minus 4, which tells us the zeros are at 3 and 4. Can we generalize this for any real root of any polynomial? And the answer is yes. Okay, so for this guy, let's find a polynomial with roots at 0, 1, 2, 3, and 4. So you might just say, well, hey, can we just write this like y equals x minus 0, which is just x minus 1, x minus 2, x minus 3, x minus 4? Yes. Feel free to check this in Desmos. But yes, this is a polynomial with those roots. So which means we have 1, 2, 3, 4, 5 roots. And y'all, if you were to actually distribute this, what would the degree of this polynomial be? If you need help, you can use Wolfram alpha, because this is a lot of different terms to multiply together. But maybe you can see it. The highest degree would just be when you multiply all of these x's together, which would be x to the 1, 2, 3, 4, 5th power. So this 5th degree polynomial has 5 roots. And that, y'all, is the fundamental theorem of algebra. It's part of it. This fundamental theorem of algebra says that, well, one part of it is that a polynomial, maybe I can write this down so that you can visually see this too. A polynomial of n degree has at most n real roots. At most. That means it can have less. So let's say an x squared polynomial might have less than 2 roots. We might only have 1. But we will never have 3. That will not cross the x-axis 3 times. So I can show you. The case with a quadratic where it only crosses the x-axis once, well, here's one. That's 0, 0. But we can also add this guy, and then we don't have any roots at all. Any real roots. But I'm not sure if you've learned about this or not, so this is new to you. Awesome. If it's not, it's still awesome. Okay. So to find the zeros, we're trying to solve for x when y is 0. So algebraically, this is literally 0 equals x squared plus 1. Subtract 1 from both sides, and we get negative 1 is equal to x squared. So we square root both sides. This means that negative 1 square root of negative 1 is equal to x. Hang on. And I forgot my plus or minus. This means that plus or minus square root of negative 1 is equal to x. But y'all, this is imaginary, right? This is an imaginary number. The definition of the imaginary number I is the square root of negative 1. So this means this root is at plus or minus I, which doesn't show up on a real field because this coordinate plane deals with real numbers only. We don't have imaginary numbers here. And there's this whole other plane of geometry dealing with complex numbers. That's fascinating. But this is where these roots will show up on that field. So, and it's actually funny because this imaginary number I came to be when there was this race to find a formula for the cubic roots. Because, for quadratic roots, we have the quadratic formula that we can use. And there's actually a formula for cubic roots, too, which is super long and awesome. And I'm going to show it to you. But I won't expect you to use it or do anything with it at this point in your mathematical education. But that's where I came to be, is when they were finding roots of cubic polynomials and found interesting things, like you could take the square root of negative 1. But we didn't have a rule for that yet. And then it ended up being applied to quadratic equations as well. So, okay, my point in that whole trail that we just took is that a polynomial of n degree can have at most n roots. So this quadratic, this polynomial of 2 degree, can have at most 2 roots, but it might only have 1, and it might have 0 real roots, is what I'm talking about when I say roots. We're talking about real number roots, but there will be complex roots, which is cool. All right. So if you're interested, I do have some of the history here. Oh, what degree? Okay, so we already talked about that. Oh, sorry. Okay. Let's go back. Can you find a polynomial with larger degree of the same roots? How about smaller degree? The answer is, with this one, this was a 5th degree polynomial, if you remember. We can find a polynomial with larger degree with the same roots. We can just add some more roots, and it has the same roots plus some extra, or maybe not. But with smaller degree, the answer is no, because you can't have a 4th degree polynomial with 5 roots. It's just not possible. So the conclusions we can make is just what I just said. And the fundamental theorem of algebra is that a polynomial of nth degree can have at most n real roots. And fundamental theorem of algebra. Okay, and now here's where I go into the history. So honestly, if you're not interested in this at all, you can just skip forward until I stop talking about it. But just for the sake of getting a whole picture of mathematics, mathematics is very rooted in history. And the mathematics we learn is actually a product of our culture, and our culture really depends on the white Western European history. So that's a lot of what I'm going to tell you, and I'm going to tell you what I know about non-European polynomial history. So let's go. So fundamental theorem of algebra has a lot of roots. It's talking about complex numbers and complex roots, which I mentioned earlier. So every polynomial with complex coefficients has a complex root. These are just equivalent statements. So you can read through these. So this means every polynomial of n degree with complex coefficients has n complex roots counting multiplicity. So this just means a polynomial of n degree, whether or not your coefficients are real, because real coefficients go inside the complex field, they'll have n complex roots. So a combination of complex and real roots, which is what we talked about. So we'll keep talking in the history of this. Finding the roots of polynomials. We have the quadratic formula for quadratics. And this awesome thing is to find the roots of a cubic function. So we got Niccolò Tartaglia, which is what he was, an Italian mathematician. So given this cubic equation, ax cubed plus bx squared plus cx plus d equals 0, you can find the roots 1, 2, and 3, using these 3 formulas, which I won't ask you to know or even remember, but there are formulas for cubic functions, and if you would ever like to have a side project and learn how to derive it, let me know. Yes, this was a big discovery in mathematics that wasn't super long ago in terms of, the history of our world, but we'll keep going. So people thought, OMG, we've been working only with quadratic roots algebraically because we had this quadratic formula, and now somebody discovers, it was a lot of different people working together. They find this cubic formula. They say, okay, well, how about with equations of n degree? Are there formulas for those functions as well? And this was actually disproved about 200 years ago. Alright, so we've got lots of big names that worked on finding these roots of polynomials, including Leibniz, which is honestly our big European calc person. Calculus has really big roots for what we teach in Western Europe and in India. So Leibniz is a really big European guy. He's French. I believe he's French. We got Gottfried, we got Euler, and we got D'Alembert. These all worked on finding the roots of polynomials. This is just a battle of different people trying to find them. We got big names here. We got Gauss's method. So this is just Gauss he worked off of other people's work for writing the fundamental theorem of algebra. This is what this was talking about. Though not rigorous by modern standards, that means our proofs have gotten stronger for the fundamental theorem of algebra. Gauss, he's also a big European math guy that shows up in the history of the math that we teach. He criticized all these other guys. Lagrange is another big name. He gave his own proof. Gauss's method wasn't to calculate a root, but to demonstrate that, hey, it exists. It's there. So, of the polynomials. So, while we don't have formulas for any of the, I shouldn't say for any, but for some of the higher order degrees, we can figure out if they exist using the fundamental theorem of algebra. And now, before we go to the notes, I want to talk about this guy, Omar Khayyam. He is from Iran. I'm saving the best for last here because this mathematician, oh man, he was forever ago, 1100 BC, or not BC, AC. So year 1100, I think, or somewhere around there. So way before all these European guys were finding out these things. So in the cubic equation, he proved the roots of a cubic equation using geometry. He created a geometric proof, which is fascinating and honestly light years ahead of these European men. So you can read through this, but this is a geometric proof. So some things in algebra we can prove geometrically, which is why one of the reasons why this school chooses to teach algebra and geometry together, because of the intricate connections between these two subjects and how one really doesn't exist without the other. So this algebraic cubic function roots can be proven using this geometric proof using circles and these quadratics actually right here and here. So that's just some of the history of these polynomials. So, all right, we'll go back to the notes. All right. So, if you listened to all of that, thanks for listening. If you have any questions, let me know. Mathematics history is something that I'm still learning about, but I really would like to share it and share the world history and try to, as best I can, to branch off of the limited European picture that our basic Google searches will give us. Because it's just not the whole story. And there's such impressive mathematics centuries earlier than when Western European discoveries were made all around the world. So, okay. All right. Okay, basic notes. Determining end behavior. Determine the end behavior of each function as x approaches infinity and as x approaches negative infinity. So what we're going to do is go ahead and graph these. If you do some experimenting, though, you wouldn't have to graph these because you'll see that this is x cubed, which will look something like that. So maybe you could already tell me what x will do as x approaches infinity and x approaches negative infinity, but for the sake of covering all the bases, we'll graph this. Hey, look, it looks like this. So as x approaches infinity, what happens to the y values? It goes to infinity as well. How about as x approaches negative infinity, which means x goes left? What happens to y? It approaches negative infinity. So I'll write that down. So as x approaches infinity, y approaches infinity. And then we got as x approaches negative infinity. In this case, y also approaches negative infinity. All right, now for the second one. I already have graphed for you. This looks like this. Okay. And this is where horizontal asymptotes will come into play. So take a look at the degree of the numerator and the denominator. They're both 3, which means the horizontal asymptote is at the ratio of the coefficients. So that means our horizontal asymptote is at the ratio of the coefficients, so 4/2, which is 2. So that means we have a horizontal asymptote at 2, which means this graph will approach 2 as y approaches infinity, and as x approaches infinity, as x approaches negative infinity. So I'll go ahead and write that. So as x approaches infinity, y approaches 2. And then at, that's strange. As x approaches negative infinity, because it's a horizontal asymptote, y will also just keep approaching 2. So you wouldn't have even had to graph this one because you maybe saw, hey, these degrees are the same. Therefore, the horizontal asymptote, which is what the graph approaches as x approaches infinity and negative infinity, is 4/2, which is 2. Or you can graph it and check it out. Okay, now this guy, this last polynomial, 5x to the 4th minus 6x. Oh, minus 6x. Totally. All right. Okay. And we got this guy. Whoa. And this is also what we're talking about when I was talking about with the roots. This only has 1 root here, even though it's degree 4. It could have 4, which means it has 1 real root and 3 complex roots. Okay, so I can zoom out so you can see, where does y go as x approaches infinity? As x goes right, y goes to infinity, and then as x approaches negative infinity, y also goes to infinity. And y'all, functions with an even power will face up or face down depending on if this first term is positive or negative. So if you have a vertical flip or not. A vertical reflection is what I'm looking for. So for even degree functions, even degree polynomials, they'll either both approach infinity or both approach negative infinity. But for something that's an odd power like this one will approach infinity and one will approach negative infinity. Okay, so for this guy, they both approach infinity. So as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y approaches infinity. Which, so if you know the rules, what each graph will look like, you wouldn't have to actually graph these. You can just say, I have a positive coefficient, it's x to the 4th, which means it'll look something like this, and it doesn't matter what this middle part does, because the end behavior will be the same, no matter what. Okay. Well, let's keep going here. And I do apologize, this video is going to end up being quite long, but thank you for sticking with me if you stayed along this whole time. This will be the only video of this week, actually, so you have that to look forward to. Characteristics of polynomial functions. So this is actually where we're going to talk about what I just talked about. Determine the minimum degree of the function, and if the leading coefficient is positive or negative. And to do this, we're going to look at end behavior. Because like I said, if it's in even degree, it's either going to look like something like this or something like this. And whatever that middle part is doing, it's irrelevant. Even degree will always look like this or this. Sometimes it's smooth if it's just a quadratic, sometimes it's bumpier. So, for our first one, as x approaches infinity and negative infinity, both of our y's will approach infinity as well, which means it has to have an even degree. But now, what is the minimum degree? And this is really going to depend on how many turns we have. So how many times we switch from being concave up to concave down. So you see, or how many times we switch from increasing to decreasing. Yeah, let's do that instead. So here, we're decreasing, and then we switch to increasing, and then we switch to decreasing, and then we switch to increasing again. So really just the numbers of these arrows can help you determine the degree of the function. So since we switched from increasing to decreasing, or vice versa, 4 times, the minimum degree of this is 4. It can be higher than that, but it can't be anything smaller than this. So the min degree is 4 for this one. And then the leading coefficient. Are you okay if I say leading coefficient like this? Is this positive or negative? Well, it depends if this the y values approach infinity or if they approach negative infinity. Ours approach infinity, so the leading coefficient is positive. If this would have pointed down, then the leading coefficient would have been negative. Okay, how about the second one? Let's see. You know it's not x cubed. You know it's not x squared. Doesn't look like those graphs. Those are graphs we know. So how many turns do we do? How many times do we switch from increasing to decreasing? So we're increasing until we get to here. Then we decrease. Then we increase. Then we decrease for a little bit. Now we increase again. So how many times do we switch from increasing to decreasing? 5 times. So this means the minimum degree is going to be 5. And then the leading coefficient, positive or negative, odd degree. Sorry, this is messy. Odd degree, if the leading coefficient is positive, will look like this. If it's negative, then we'll go the opposite way. So the leading coefficient for ours, since as x approaches negative infinity, y approaches negative infinity, those match up. This leading coefficient is positive as well. Let's see, another way you can think about this is, no, never mind. Okay, next one. Let's see. As x approaches infinity, y approaches infinity. As x approaches negative infinity, y approaches infinity as well. So this is going to be an even degree for sure. But then how many different turns do we have? So we got 1 here, we increase slightly here, we decrease, and we increase again. So this is also going to be a 4th degree. Minimum degree is 4 again. The leading coefficient. This opens up and not open down. Overall, this is also going to be positive. Wow, I didn't give you any negative examples. Hopefully you'll be able to tell if a polynomial looks like this, then you will have a negative leading coefficient. All right, and that's it for that. So let's keep going here. Okay, and this is where we're going to use the roots. So we already actually talked about this. So write possible functions for the graphs. So possible functions, we can use our roots. But also, keep in mind, we go increasing to decreasing to increasing, so this could have a minimum degree of x cubed. So we can use our roots. So this -2 is telling us that our roots are at x equals -2, 3, and 5. So we can just write this as y equals x minus -2, which will become +2, times x minus 3, times x minus 5. If you type that into decimals, you will get something that looks something like this. So I went ahead and graphed this. And y'all, if I zoom in here, our roots are where they need to be. They're at -2, we got 3, and we got 5. So that's good. But This curve is supposed to be all the way down here at 7. So we can actually make this a little bit closer by multiplying by a term to get this to be compressed a little bit. So one way to think about this is when x equals 0, because this is the x-axis, or this is the y-axis, when x equals 0, we want y to be 7. So let's, we want 7 to equal something times 2 times 3 times 5. But actually this will be -3 and -5, right? Which means that we want 7 to equal some number times 30. So to do that, just take 7 divided by 30, and that'll get us that number. So that number is 7 divided by 30. So we can do 7 divided by 30 right here, and then hey, that's what we needed. We got that point to be at 0, 7. So our function here can actually be, to be even more exact, so we got the roots there, to be y equals 7 over 30. X plus 2, x minus 3, x minus 5. So this part covers the roots, and then this part covers where we want this line to go. So let's do this next one. Write in factored form the equation of the polynomial graph below. All key features are shown. So let's find the roots. When x equals -2, 4, and 5. So we know in our equation we're going to have, again, x plus 2, and then x minus 4, and x minus 5. So let's go ahead and type this guy into Desmos and see if it crosses at, oh goodness gracious, 2, 3, 4, 5, 6. Okay, so it's low, so this will be 11. Nope, it'll be 10. We're looking for 10. Okay. Goodness gracious. So we're looking for y equals something times x plus 2, x minus 4, and then x minus 5. All right, we want this to be crossing at 10, not 40. So what we can do is take, when x equals 0, so this will be 2 times -4 times -5, 40. So this means we want y to be 10 when x is 0, so this is going to be 10 times something, 10 to equal something times 40. What is that something? Well, 10 over 40, 1/4, because 1/4 of 40 is 10. So this means if I throw a 1/4 right here, we will now cross at, 10, 0, 10. Which is exactly what we wanted, even though this graph is a little bit goofy, so this is 110. X plus 2, x minus 4, x minus 5. So what's really important are the x-intercepts and the y-intercept. That's how we're really going about solving this. And what degree it is. So our function that we wrote is degree 3, and this one is also degree 3 up here because we start low and then we go up high, so we go from third quadrant to first quadrant. And that's how you can write polynomial functions given graphs. There's lots of things you need to know, but the key are the roots and then the y-intercept, and knowing how to write a function based on that information. Right, and okay, we've got just a couple things left. So, asymptotes. I'm just going to do these algebraically, and I'll let you decide end behavior. So, asymptotes. Vertical asymptote is when the denominator is 0. So we have one when 2x equals 0. We have a vertical asymptote when x equals 0. Boom, done. Horizontal asymptote. We have one of those guys if the degree of the numerator is smaller than the degree of the denominator. Hey, our degree of the numerator is larger, so we actually don't have one. Not applicable. And you can double check in Desmos here. Now this guy. We have a vertical asymptote when the denominator is equal to 0. Which is when x squared equals 9, which is plus or minus 3 will get us those vertical asymptotes. So we actually have 2 in this one. And yeah, we have a horizontal asymptote if the degree of the numerator is smaller than or equal to the degree of the denominator. And our degrees are the same. So it's actually the ratio of the leading coefficients, which are both 1 and 1. So we actually have a horizontal asymptote at y equals 1. I guess I should have written. We have a vertical asymptote at x equals -3 and x equals 3. So those are our asymptotes. And we already did end behavior, but if you would like to check your work, feel free to email me your responses to that question. Okay, let's keep going. Let's do these last couple of problems here. So, question. After running 4 miles at a speed of x miles per hour, a man walks another 4 miles that was 2 miles per hour slower. Express the time of the trip as a function of x, and then what horizontal and vertical asymptotes exist? So, x is our speed, and remember that speed is distance over time. So I'm just going to write x is our speed is the distance divided by the time. Therefore, time equals distance over speed. So that means time equals distance over x. Okay. And actually, I've got a little typo here, a function of time. So, yeah, okay. So, we run 4 miles at a speed of something, and then we walk another 4 miles that was 2 miles per hour slower. So this is really x minus 2, 2 miles per hour slower than this x. So we can write this actually just like this. The time spent is going to be the ratio of this first trip plus the ratio of the second trip. So we're going to write the distance over the speed, which we don't know, which is x. So it's going to and then if we add it to our second part of the trip, we walk another 4 miles. It's 2 miles per hour slower. So we go 4 over x minus 2. That's our function of time. That's the time of the trip as a function. Oh, excuse me. This was correct. This is a function of x. Okay, well, that disappeared, so I'm going to rewrite that quick. So the time of x is going to equal 4 over x plus 4 over x minus 2. And that's it. So now what horizontal and vertical asymptotes exist? Let's go ahead and graph this, and let's see. So we've got 4 over x plus 4 over x minus 2. We've got a bunch of these. We've got asymptotes at 0. We've got a vertical asymptote at 0, which accounts for this one. And then we've got vertical asymptotes at 2. That accounts for this one. And we have a horizontal asymptote at 0. So we'll talk about that. We'll talk about the algebraic reasons why. So we've got vertical asymptotes at x equals 0 because that's when this function is undefined, and at x equals 2 because that's when this function is undefined. And our horizontal asymptotes, remember that's when the degree of the numerator is smaller than or equal to the degree of the denominator. Both of our numerators' degrees are smaller than the degrees of their denominators. Therefore, we have horizontal asymptotes at y equals 0 for both of them, which was shown on the graph when you graph it in Desmos. And that's it for that one. So we'll just go ahead and keep going here. Do the last problem, and then that'll be it for the video. So Delia runs the 3.1 miles from home to the park at 6 miles per hour, and then she hops on her bike and returns home in 12 minutes. Let's sketch a graph of her distance from home as a function of time. find the slope of each segment. We'll assume that she hops and just gets going right away. And then, what does it mean to say that Delia's velocity is inversely proportional to the time she takes for her ride or run? Okay, so let's first graph this. So we're starting at time equals 0, and this is the distance over here. And this is the time in let's see. Let's do minutes. Okay. So our distance away from home. So we're starting at home. So we're actually starting at home when time is 0. Because remember, this is our distance away from home. So this is our first point. Now she's running 3.1 miles from home to the park at 6 miles per hour, which means she runs 3.1 miles at 6 miles per hour. Which means it took her 3.1 miles divided by 6 miles per hour, which is about 0.52 hours. So we'll say this is about 60. This is 31 minutes exactly. So she took 31 minutes to go from home to the park. So I'm just going to mark that here. Let's say this is 31 minutes. And constant rate of 6 miles per hour. And then this point would be 3.1 up here. Okay. Now, she jumps on her bike and comes home in 12 minutes. So that means 12 minutes after this 31 minutes, which will be 43 minutes, she comes on home. Okay, so this is part A. This was our graph. Find the slope of each segment and interpret their meaning. Okay, I'm going to go ahead and erase this. So the slope of the first segment, I guess we can find it. Change in y over change in x. So segment 1, we can just call this segment 1, and then we'll call this segment 2. This is for part B. Okay, so the slope, change in y, well, we go from 3.1 to 0. So this is just 3.1 minus 0. Change in x, well, we start at 0, we go to 31. So this change in y over change in x, which is 0.1. So this means she goes 0.1 miles per minute, which if you were to convert that to miles per hour, we take this 0.1 times 60, which is the same thing as 6 miles per hour. And y'all, this means that the rate equals the slope. This is one of the biggest topics in calculus, that the rate of your situation is equal to the slope of the line, which you likely know already. Okay, so segment 2, change in y over change in x. This is change in y. Same thing, actually. We start at 3.1 this time, we go to 0. Actually, I need to do it like this, 0, 3.1, and then time 43 minus 31, which is negative 3.1 over 12. So this means she went 3.1 miles in 12 minutes, which is 0.25-ish to 6 miles per minute, which is the same thing. I'm going to multiply this by times 60 to get 15.5 miles per hour. So again, the slope of the line is the rate. That's very, very important. Or the velocity. The slope is the velocity or the speed. All right. And then this negative sign, That just means she's going back towards home. That's what that means. We go back to our original position. So, see, what does it mean to say that Delia's velocity is inversely proportional to the time she takes for her run or ride? This just means that as the velocity increases, the time will decrease. I can write that. It's getting kind of messy here, but as the velocity increases, the time decreases, which makes sense. If you run faster, it's going to take you less time to get to the place that you need to go. All right, y'all. That is it for this video. I do apologize for the length, but thank you for sticking with it and watching it. And again, this will be the last video for this week. We'll have a quiz on Friday of this week over sections 1.6 up until this point, 1.10. So email me if you have any questions at all about these notes or want to learn more about anything, or if you have any questions over anything else. All right?